Hi, thank you all for joining me this evening, afternoon, to go hear about syftr. So I'm Mark Steadman. I'm a researcher in our DR research organization, and syftr is our scientific project which we developed and published at AutoML this year, AutoML Conf this year in September, and it's built on Ray. So I'll tell you about syftr and give you an introduction why we built syftr and why we use Ray. So at DataRobot, we've worked with a whole bunch of customers, and we've saw the same issues again and again and again with people building agentic AI. They had issues around quality. They had issues around latency. They have issues around cost. And so they want to know a way, can I find what is the right workflow that might explore the space? And then it's like the Red Queen in Alice in Wonderland, because every single time they do it, 3 months later, a new model comes out, and they have to start the process again and again and again and over. So this is what blocks people from actually getting value, because then they go back and the person to the stakeholder, and the stakeholder says, well, have you tried this? And I have to go back and go do it. And that's, okay. But that's the only small space they can do. They have all these decisions you have to learn about. Not only you have to know, in this whole space here, like which embedding model? Do I use a reranker? Do I do a hide? Do I use an agentic flow? Which agentic flow? Do I use a sub-question flow? Do I use a critique or React flow or React critique update flow? All these aspects here, it keeps expanding. The whole space of what people can look for is expanding. And so we see from a whole space here, we can sample a single workflow here that looks like this. We built this in LLM Index. We can sample this workflow and evaluate it. But that's a very manual process right now. People are calling these all up by hand. They have to do this very small space. Can we do better? Because I said there's all this huge combinatorial space. And so that leads to two major things. The first is, can we search over the space effectively and have a strategy and a modeling strategy, which we did using Optuna? And can we have a way to parallelize this to actually get a good coverage of that space, which is what we used Ray for. And so this is presenting kind of the idea behind syftr, right? We map out the space. We allow people to define the space in YAML. They can then, what are the options they want to look over? We'll then sample and explore that space using Optuna, using Bayesian optimization, just to evaluate against accuracy versus cost, or accuracy versus latency, that whole space. Take these flows, build out this Pareto front, evaluate it, then decide where to go next, keep exploring. So this is sort of the underlying idea behind syftr, to make this a very easy way to do, to kind of explore the space. This is what it looks like in action. You can see here, it's kind of picking out each of the spaces. On the vertical axis, you have accuracy, which we're using in this case here. It's quite a Q&A problem, so we ask the questions. And then people have set up LLM as a judge to go evaluate how good is this particular answer. And on the y-axis, on the lower axis, right, on the x-axis, you have the cost. And the thing about this space, which is really interesting, is that these can vary dramatically in cost. This is in the log space. So the cost of these different flows, going from like a simple flow to an agentic flow, can be thousands, it can be over 1,000 or 10,000 difference in cost, right? So one of these flows in production might cost $1, and something else might cost $10,000, right? And you want to know what's it worth? What's it worth? And at the same time, you also might have different things. So for example, one problem might be, you might say, hey, a good strategy is to cut down my token count in a really expensive synthesizing LLM by using a lot of other LLMs to kind of break down the question and be very selective about which data to retrieve from a vector database. On the other hand, you might say, hey, it might be much cheaper just to throw a whole bunch of context into an LLM and let the LLM figure it out, right? And which of these approaches better, which of these actually gets better results, and which of them gets better, what's the cost trade-off there? Isn't necessarily obvious, because again, inside that space, you have, hey, okay, so you say, I want to break down this down into an agentic problem. Can I use a simple LLM to do this? Or do I have to pay an expensive LLM? And so we see this kind of very interesting space problems here around, hey, maybe these particular tasks in the space, we can save a huge bunch of money by using a simpler LLM, a small-scale LLM, to do these particular tasks because they're well-defined. The LLM can do it, And then these other parts, we need the really expensive LLM to go through and do that part of the space. And so how do you evaluate the space? So we kind of go through this, and then we use Optuna, right, underlying Bayesian optimization to build out, to go explore this kind of effectively and build out these curves. And we get results that are better than, you can get these massive differences in accuracy and scale relative to just a naive out-of-the-box pipeline. So, but we want to do this in parallel, right? We don't want to wait. We were doing 1,000 trials, for example. We don't want to wait 1,000 hours. If each trial takes an hour, we want to parallelize it. And that's where we brought Ray in, right? We can use RayTune to run each of these flows. And this is the code that just makes it very simple to take one of these parameterization dictionaries that we get from Optuna, we sample from the space, send that to RayTune. It then is able to spin up a worker and run that. Then the worker can run, in this case here, because we've offloaded all the expensive steps, the LLM computation into a VLM server, the embedding into a VLM server. So these workers can be very, very light, running on CPU, running a lot in massive, in a kind of very matter-of-possible way, where they go, go all running in synchronous and kind of this very highly distributed fashion, running in there. And then Ray will then manage the whole lifecycle of these workers that are running, and they may take at very different times, because some of the jobs run quickly, some of them take long, manages to run it back, and that worked out very well. And it's also very lightweight. We want this to be a simple package that people could install on their laptop and run in the laptop when they're developing Explore, or run in a small research cluster environment. They didn't want to have to go set up a Kubernetes cluster and go figure out how to get Kubernetes running on it and then get we want it to be something which is very simple. And so this is what kind of looks like a run. And this kind of leads to one of the main first problems about doing an agentic AI workflow. The first issue you have is that these things actually kind of have errors, and you have to kind of understand what's going on there. Couple of unexpected errors we've seen are things like, hey, this particular flow generated a content moderation error by your cloud provider. Why did it generate that collaboration? Why did it generate that error? What was about that particular answer or step in that process that triggered a moderation flag, for example? So we have to dig into that and see those errors and see, hey, that's actually what's going on here. Or this particular flow, this particular aspect selection, triggered an issue in the tool calling. So in a lot of these stages, in all this, that we're very, very heavily relying on the tool call parsing, the reasoning parsing to work in coming back from VLLM. That might fail occasionally. Occasionally you get errors where it generates poor JSON, for example. The tool call parses errors. And so when you run these trials, you get these errors and you want to be able to dig into them. So having the observability of having all the logs together in a centralized way becomes very important, because you come back, there might be a whole bunch of potential causes that you never thought about, right? You're never like, this particular question might have triggered Azure to say, you violated OpenAI content policy. I'm asking about something very, very innocent. Maybe something you found in your database that you were not aware of that pulled out some weird content. Maybe it's something that was synthesized by the element that kind of triggered that. But being able to kind of have that very easy way to have built in, grab all those logs, dig into them, and explore them, after the fact, and understand and categorize them is very useful. And also a way to do this in a way that doesn't break the whole search. So you get an error, and then the search goes on, and if something particular failed in that space, we can then just retry that whole point in that particular space, and Optuna can resample it or a new space and move forward. So this is one of the first things we really, really liked about Ray. We actually tried to use Ray actors to do a bunch of the embedding nodes, and having a whole bunch of these embedding models crammed on a node with a GPU. We actually had lots of problems because we were asking for very, very small chunks of the GPU. So if you want to put 100 Ray actors on a single GPU, we had issues there scaling that up across the whole cluster. So that's great. So the other main issue we were looking at, and where Ray was really where we're kind of intersected with Ray a lot, was this kind of search pattern creates very interesting load on the cluster. Because Optuna will go through and start out, for example, searching a broad selection of models and embedding models and that kind of space. And then it'll kind of find things that are looking optimal, and start searching around there and honing in on there and start trying that particular point, that particular model, for example, embedding combination. You'll get this big hotspot and requests that are coming on there. And so we want to be able to manage that when we hit our rate limit from our cloud provider or backing up in the VLLM queue. So we spent a lot of time building out. The way we solved this was by putting in a very aggressive back-off strategy, because in this particular environment, we're doing exploration, we're doing development. If we wait 10 minutes for that peak to be smoothed out to meet the request load and it finishes, that's great. If we wait an hour for that peak to smooth out and meet a request there gets done, that is awesome. But the way to do that is we would build in this very expensive retrying back-off policy, such that we do not have to have a lot of communication between the different rate workers. They'd kind of convert in a spot, and then VLM, they would start getting timeouts or long requests, then they naturally back off and they kind of manage the load themselves. We looked at using RayServe to do this because we thought this would be a great way to reutilize the cluster. So instead of spinning up, hey, I want to try 6, I have 8 GPUs, I have spin up 8 models or 3 models or whatever, and have them in parallel, maybe I could get 8x the that kind of throughput there at a particular point by having the cluster be able to reallocate the load among the different models inside VLLM. So basically, maybe you could launch that and have the VLLM launch these things run using RayServe and run directly on there and get benefits that way. Maybe you could have this here. The challenge is we were making very heavy, we really needed the VLM server because we're losing all the components that are in that infrastructure and that tier, right? So when we were doing this, we would have the tool call parsing, the reasoning parsing, the extraction of the tool calls and requests is all happening inside the VLM tier for these various models, and we have to actually dig into a lot of these things themselves because some of them did not do this correctly out of the box. For example, they provide chat templates that did not inject the tools into the LLM. So we had to do all this configuration, and these configuration settings are only available in the front end of VLLM. They're not available inside the VLM engine itself, and so when RayServe would run fine on VLM, we try the same configuration with RayServe, and it would not be able to understand what the configuration is because that is not relevant to the VLM engine, actual model execution engine itself. So that was not successful. But hopefully that's something we can get work on in the future, because I think this is a really interesting way of thinking about how to use a cluster of GPUs effectively to manage the workflow. So I think that's an area I'm really looking forward to. Hopefully, collaborate. People can sort of get inspired and think about ways to help improve this type of infrastructure for us in the future. So I said, yeah. So, to kind of come to conclusions, that we have this search that was able to kind of very efficiently, very effectively do the space. We published this at our RLML conference. The paper is right here. We can read that paper yourself. You can dig into some of our results if that's what you're interested in. But also, we thought that was a really interesting use case for using Ray. So that's why we decided to come here, present it, and hopefully you enjoyed it. So, thank you, and I'm happy to take questions.
Thank you, Mark. Does anyone have any questions for Mark while he's on stage? Got a couple here.
Thank you. Very exciting, very interesting tool. It's basically like AutoML for RAG and agentic pipelines. Oh, speak more. Okay. Can you hear me?
Yeah, I can hear you.
Okay, great. Couple of quick questions. One is, what sort of use cases has syftr been applied to that you have seen actually produce better agentic pipelines, RAG pipelines? And two, what are the eval metrics that you showed accuracy? And I looked into the paper, it uses LLM as judge. What are you seeing among your customers in terms of eval metrics and how the Pareto frontier changes for different eval metrics in the optimization procedure?
Yeah, no, so that's a great aspect. So a couple of things here. So first of all, it is an open source package, and people can go look at the code themselves and run it, and then we don't necessarily know that people are using it. The paper was focused on agentic RAG, so we were using it for RAG, as kind of like the case, because that's where we thought there was a lot of good benchmarks, and so we could compare and show how this does compared to other solutions out there. So in the paper, we talk about, for example, comparing to Amazon Q, for example, or Azure Assistant and how that compares to that. So things like that. So that was where we were looking at. We are kind of moving, one of the aspects I think is kind of looking more towards, that was kind of where we were when we wrote the paper. We're moving towards looking at things like software engineering, for example, where we have more clear rewards. And so you might do things where, you did it to complete the task successfully, or other agentic workflows that do that. And that's an area where we're looking at expanding. In terms of getting into production, that is an area we're doing inside DataRobot and working on getting it into our product and actually getting out to customers. We have people who explored it and then using that themselves, but then actually getting that as something which is really easy for people to get up to and go.
All right. Thank you very much, Mark Steadman from DataRobot.